Alright, very good day to you. Today we are looking at chapter 7.3. So this is the last break for chapter 7, chapter 7.3. I need to look at types of intermolecular forces. So before this, we have looked at different covalent molecules. We talk about some molecules are polar, some molecules are non-polar. And we say that if a particular molecule is polar, there is a very high chance is because of the difference in electronegative value if you are talking about diatomic molecule, which means that if you are talking about dipole-dipole forces, then you talk about these forces are present, or there is a net dipole moment, or there's a net dipole force in a polar molecule. So three types of intermolecular forces. We have dipole-dipole forces, we have hydrogen bonding, and we have dispersion forces. We will investigate each and every of these types of intermolecular forces. I'm moving on to the next slide. And make sure you're on page number 167. So this is on page number 167, and we'll be looking at the three types of intermolecular forces. I'm moving on to the next slide. So dipole-dipole forces. You see, dipole-dipole forces only occur in polar molecules. Once again, when we talk about dipole-dipole forces, we are talking about a net dipole moment. Alright, do not get confused. In the last few lessons, when we talk about dipole moments, we say that if you're talking about polyatomic molecule, some polyatomic molecules are symmetrical, even though they have individual dipole moments, but because it's symmetrical, it becomes non-polar as a result. So in this case, we are purely talking about those net dipole moment as a whole. As a whole, is there any net dipole moment? If there is net dipole moment, then in this case, it only occurs in polar molecules. So when you talk about those partially positive, partially negative, the one that we discussed in class, we know partially positive is attributed to partially negative. As you can see here, partially positive is attributed to partially negative, and partially negative is attributed to partially positive of another molecule. So intermolecular forces, as you can see here, is referring to the force between, in this case, two different molecules. So not within the same molecule. Within the same molecule is a covalent bond. Between different molecules, we are talking about, in this case, dipole-dipole forces, which is a type of intermolecular forces. So we say these forces result from the attraction between positive and negative ends of polar molecules. Moving on to the next slide. So dipole-dipole forces are relatively weak since the partial charges, partially positive and partially negative on the molecules, are small. The molecules are more polar when there is a greater difference in electronegativity of the atoms, or less asymmetry in the shape of the molecules. Molecules are more polar. Have stronger dipole-dipole forces. So once again, when we are talking about dipole-dipole forces, it exists in a polar molecule. If the molecule is more polar, it means that there is a greater difference in the electronegativity value. And it says that molecules that are more polar have stronger dipole-dipole forces, which is true, because if there is a greater difference in electronegative value, there will be a greater dipole-dipole forces that exist between those polar molecules. So they are weak to begin with. Intermolecular force is nowhere close to covalent bonding. You must be very clear. We talk about polar molecules such as water molecule, as we have discussed when we started off on chapter 7. We say that within the water molecule we have covalent bonding. Between water molecules we have hydrogen bonds and also dipole-dipole force. I will go to hydrogen bond in a very short while. So the point here, the intermolecular force is very weak as compared to the covalent bonding. But the more polar that particular molecule is, the greater the dipole-dipole forces that exist between the molecules. Move on to the next slide. So the strength of dipole-dipole forces in molecules, so we are still on page 168. The strength of the dipole-dipole force in molecules is directly related to the melting and boiling point of the substance. The stronger the dipole-dipole forces, the higher the melting point and boiling point. This is because the dipole-dipole forces bond the molecules together in the solid or liquid. Stronger dipole-dipole forces require more energy to break these bonds and change the solid to liquid or liquid to gas. You say, for example, compare methanol CH2O and ethane CH3CH3. Alright, as you are probably aware, methanol is asymmetrical based on what we have discussed previously in the last few lessons. The methanol structure looks something like this. At the bottom of this particular PowerPoint, this is the structure of methanol CH2O. We know methanol is asymmetrical and is a polar molecule. If you are comparing it in this case to ethane, we know ethane is non-polar, it is symmetrical, it is non-polar. So the point here is that if you're going to compare between a polar and non-polar molecule, you can see a polar molecule here has a much higher boiling point. You can see a boiling point of methanol is -19, so it boils at -19, whereas the boiling point of ethane is significantly lower, which is -88.5, which means that at -88.5, ethane will boil, but methanol will remain as liquid. But methanol in this case will only boil at -19. Alright, so even though both have, considered as low boiling point, but because ethane in this case is non-polar and methanol is polar, and we know that dipole-dipole moments does increase the melting and boiling point of a particular substance. Why? Because the intermolecular forces does play a role. The greater the intermolecular forces, the greater the dipole-dipole forces that exist, which means that it's harder for the bond to be broken. Alright, so once again, a polar molecule, generally speaking, they do have a higher boiling point than a non-polar molecule, but bear in mind we do need to look at take other factors into consideration, such as the size of molecules and so on, that we will discuss in a short while as well. So we move on to the next slide. So hydrogen bonding, it says here, hydrogen bonding is a special form of dipole-dipole force. Hydrogen bonding only occurs between molecules in which hydrogen atom is covalently bonded to an oxygen, a nitrogen, or fluorine atom. Oxygen, nitrogen, or fluorine atoms are small and highly electronegative. It says, therefore, they strongly attract the electrons in a covalent bond. This creates a significant partial positive charge on the hydrogen atom bonded to this atom. The partial positive charge hydrogen atom is then attracted to the lone pairs of electrons in the nitrogen, oxygen, and fluorine atoms of neighboring molecules. It says the result is a relatively strong intermolecular bond that is approximately 10 times stronger than a dipole-dipole bond, but about 1/10 the strength of ionic and covalent bonds. Once again, we are doing a comparison between ionic compounds, metals, and covalent molecules. By covalent molecules, there's also another category known as the covalent lattice structure, but we're not going into detail on that. Covalent lattice structure generally are covalent molecule, but they are a lot bigger, which means that you can sort of predict saying that their melting and boiling point should be significantly greater than a covalent molecule. So coming back to this, when we're talking about hydrogen bond, the criteria for hydrogen bond, and you must be very clear, criteria for hydrogen bond here is that hydrogen bond is a special form of dipole-dipole force, so it's a type of dipole-dipole force, and hydrogen bond exists when there is a hydrogen atom that is covalently bonded to an oxygen, a nitrogen, or fluorine atom. So that's number one. And number two is probably mentioned here as well. You need to have the lone pairs of electrons. Lone pairs of electrons in the nitrogen, oxygen, and fluorine atom. So if you are going to look at a molecule that has hydrogen bonds, such as water molecules, going back to water molecules, is a polar molecules. We know that water molecules has two lone pair electrons. It has the tendency of forming the hydrogen bond. Why? Because of the presence of that two pair electron, and because hydrogen is being bonded in this case to oxygen. So if you come across a hydrogen to oxygen, hydrogen to nitrogen, or hydrogen fluorine, and that particular structure has lone pair of electrons, there is a very high chance it can form a hydrogen bond, or more than one hydrogen bond. So it says here that this hydrogen bond is relatively strong. It's 10 times stronger than dipole-dipole bond, but it's still weak as compared to ionic and covalent bonds. So you have to be very clear. Which is why when I was talking about water molecule, I was saying that water molecule consists of covalent bonding within the molecule, but between the molecules we have hydrogen bond. The covalent bond is a lot stronger, it's 10 times stronger than the hydrogen bond. So if you are going to melt an ice or going to boil water, you know that what has been broken is the hydrogen bond, not the covalent bonding. So something that you have to be very clear. Moving on to the next slide. Alright, as you can see here, these are the different examples. We did discuss this in the last few lessons as well. So if you look at ammonia, you know that there's each ammonia molecule has one lone pair electron, as you can see here. And hydrogen bond between ammonia molecules exists because of that one pair electron, and is bonded in this case nitrogen to hydrogen. In that molecule, water molecule, you have two lone pair electrons, so the one on the right is bonded to another water molecule. Oxygen is bonded to hydrogen, that's hydrogen bond. Third one, hydrogen fluoride, is to know hydrogen fluoride has 3 lone pair electrons, and you must have hydrogen bonded to fluorine. And the last one is showing the hydrogen bond between water and the oxygen atom of propanol, which is acetone. We talk about acetone in the next few lessons. Acetone looks something like this. So there's an oxygen that is present, CH3CH3CO, which is the structure of propanol. And you know that both of these molecule does contain lone pair electrons. For propanol, it has 2 lone pair electrons. For water molecule, it has 2 lone pair electrons as well. And you can see that hydrogen bond can form between these 2 molecules. Alright, make sure you're very clear with that. Move on to the next slide. Alright, so coming back to this hydrogen bond, how does it play a role? You can also roughly guess that if that molecule has a hydrogen bond, let's say you compare it to a molecule that can form hydrogen bond, and that molecule can then form dipole-dipole force. Most likely, that molecule that can form hydrogen bond will have a greater melting and boiling point. That is something that you have to be very clear. So since the pressure hydrogen bond results in a higher melting and boiling point, recall that ethane is non-polar, so it has no dipole-dipole forces between the molecule. Methanol has dipole-dipole forces but does not have hydrogen bonding. Methanol has hydrogen bonding between molecules because of hydrogen atom attached to oxygen. So whenever you come across a molecule that has lone pair electrons and it has hydrogen being bonded to fluorine, hydrogen being bonded to oxygen, or hydrogen being bonded to nitrogen, you know that particular molecule can form hydrogen bonding. In this case, the boiling point of methanol is 64.7 Celsius. Boiling point of methanol is -19. Ethane is -88.5. So what you can see here at the bottom, once again, you can see that if that molecule can form hydrogen bonding, which means that it has a special form of dipole-dipole force, which is in this case methanol, and you can see that the boiling point of methanol is 64.7, which is the greatest of the 3 molecules. Methanol is -19, ethane is -88.5. So the conclusion they can make here is that if that particular molecule is non-polar, is symmetric, is non-polar, it will probably have the lowest boiling point out of these 3. If that particular molecule has dipole-dipole force, it is somewhere in between. If the molecule has dipole force, it can form hydrogen bonding as well. It will have the greatest boiling point, as you can see in this example. Moving on to the next slide. Hydrogen bonding, the 2 requirements for hydrogen bonding are hydrogen atoms covalent bonded to oxygen, nitrogen, or fluorine atoms, lone pair electrons on the nitrogen, oxygen, or fluorine atoms of neighboring molecule. Alright, so make sure you're very clear on this. That's what we have discussed today. Moving on to the next slide. Alright, I'm just going to continue on this. So hydrogen bonding in water. So when we talk about hydrogen bonding in water, as you can see here, it says that one unusual properties of water is that it is less dense than liquid water. So what does it mean? It means that that particular water molecule here, as you can see on this diagram, number 1, it is of V shape. Your water has 2 hydrogen atoms attached to an oxygen atom in a V or band shape. It says therefore the hydrogen atoms can form hydrogen bonds with the lone pairs of electrons on the oxygen atoms on neighboring molecule. In this way, it says water molecule can form 4 hydrogen bonds with 4 other water molecules. So if you look at this diagram on the right, you can see that this water molecule in the middle can form hydrogen bond with this water molecule, this water molecule, this water molecule, and this water molecule. And usually you'll find the scenario of it forming 4 hydrogen bonding in an ice structure as compared to liquid water that it can form some hydrogen bond, not all of them. And then in gas, you can sort of predict, saying that it most likely it does not have any hydrogen bond, which is why it can freely move around in the environment. So that's something for you to think about. I'm moving to the next slide. Alright, so coming back to this, you can see that ice, which is the structures at the top, is less dense as compared to liquid water. Because as you'll probably agree or aware that if you look at this diagram at the top, you can see the density is lower if the volume increase. So this diagram at the top, just give me a second so I can show this to you. So this diagram, this is the structure or the lattice structure of an ice compound. Bear in mind, just for you to be very clear, covalent structures, in this case, is a small covalent molecule. So when I talk about covalent lattice or covalent giant lattice structure, in this case, water molecule is not a giant lattice structure. It's significantly bigger than that. So in this case, this water molecule is just a very small, simple lattice structure that can form in an ice structure. As compared to, let's say, in liquid water, some hydrogen bonds are present, some hydrogen bonds are not present. So in this particular case, you can see that water molecule, if we form 4 hydrogen bonds, which is the maximum number of hydrogen bonds can be formed, then most likely it will be an ice structure. Its density will be a lot lower as compared to liquid water, which is only capable of forming some hydrogen bonding. Moving on to the next slide. Alright, so we are still on hydrogen bonds in water. It says as ice melts and forms liquid water, the density of water increases rapidly. This is because the open crystal lattice collapses and the water molecules pack together more tightly. It says, however, as the temperature of the water increases further, water molecules in liquid move and vibrate more rapidly. The movement causes the molecules to spread further apart. As the molecules move further apart, the liquid becomes less dense. So the point here, you must be very clear. When liquid water is being frozen into ice, we know that the volume increases, the density decreases, which is why ice floats on the surface of liquid water. But when we are talking about ice melting into liquid water, we know that the hydrogen bonds some of them starts to be broken, the molecules start to spread further apart, and then liquid water now will be less dense as a result. When I say they are spreading further apart, which means technically saying their volume does decrease. It must be very clear. Why it decreases? Because it doesn't form that particular structure that we see in ice, which is that one water molecule is being bonded to 4 other hydrogen, bonded to 4 other water molecules through hydrogen bonding. So you do not see that 4 hydrogen bonds, and that is the reason why liquid water is a lot less dense as compared to ice, and it does not float. So what floats on liquid water will be the ice structure that we have discussed. Moving on to the next slide. Alright, dispersion forces. So this is the last intermolecular force that we're going to talk about. We have looked at dipole-dipole force. We have looked at a special form of dipole-dipole force, which is the hydrogen bond. And we know that hydrogen bonds can exist in 2 particular factors. Number 1, you must have hydrogen being bonded to nitrogen, oxygen, or fluorine. Number 2, lone pair electrons must be present on that particular structure. So when we talk about dispersion forces, and this is important, when we talk about dispersion forces, they actually exist in both polar and non-polar substances. So those substances that we have been talking about, they do have dispersion forces. Other molecules, such other non-polar or non-polar molecules in general, even though they don't have dipole-dipole force, they don't have hydrogen bond, but they can form dispersion forces. You must be very clear. So non-polar molecules such as oxygen, nitrogen, fluorine, for example, these molecules, even though they are diatomic, they consist of atoms of the same element. We know that they are non-polar because they have the same electronegative value on both sides of the atom. So these moves are caused by temporary dipoles in the molecules that are as a result of random movement of electrons surrounding the molecule. These temporary dipoles are also known as instantaneous dipoles. So temporary dipoles are known as instantaneous dipoles. Bear in mind, instantaneous dipoles are not the same as permanent dipole. When we talk about dipole moment, the one that we discussed at the start of today's lesson, those are known as a permanent dipole. When we are talking about dispersion forces, it only exists in this case, or it exists in both polar and non-polar, but it forms this temporary dipole that we're going to discuss, which is a random movement of electrons, right? Random movement of electrons surrounding a molecule. So how does it look like? If you look at this particular diagram here from the textbook, it says in the molecule, the electrons are constantly moving. In the case of non-polar molecules such as fluorine, the electrons spend equal amount of time around each atom. Occasionally, the electrons gather more closely together at the end of molecule, causing one end of molecule to become negative and the end to become positive. This is known as temporary dipole. Bear in mind, temporary dipole is not the same as permanent dipole. When you talk about dipole moment, we are talking about permanent dipole. Temporary dipole in this case exists in both polar and non-polar molecule. In this case, this is a non-polar molecule. But what it's trying to say that because electrons constantly moving, its electron is not static. As you probably agree with me as well, electrons can move. So in this case, electron will be moving from the left towards the right, from the right towards the left, and because the electrons constantly move, it will form what we call temporary dipole. So it's not permanent dipole, that's why it's called a temporary dipole. So this temporary dipole can induce dipoles in the neighboring molecule. So, and I move on to the next one. I said the neighboring molecules can then induce dipole in their neighbors. The temporary dipoles attract each other to create the intermolecular forces known as dispersion forces. So these dispersion forces do exist in both polar and non-polar molecules. Why is it important for us to talk about dispersion forces? Because dispersion forces do play a role. It does affect the melting and boiling point, even though it does not have such an effect that is as great as the dipole-dipole moment or hydrogen bonding, but it do play a role. The larger the molecules, as you can probably expect, the higher the melting and boiling point. Why? It has also a lot to do with these dispersion forces for molecules, for both polar and non-polar molecules, of course, but especially for non-polar molecules. The greater the size of the molecule, the greater the dispersion forces, so the higher the melting and boiling point. That's what we should expect. Once again, this temporary dipole is known as an instantaneous dipole. It is not the same as permanent dipole. Moving on to the next slide. Alright, strength of dispersion forces. The strength of dispersion forces increases as the size of molecules increases. So it says larger molecules have a greater number of electrons, therefore it's easier to produce temporary dipoles in molecules with larger number of electrons. Since larger molecules have stronger dispersion forces, they have higher melting and boiling point. As probably agree with me as well. When we're talking about a molecule, the greater the size of the molecule, the higher or the greater the dispersion forces, the higher the melting and boiling point. Moving on to the next slide. Alright, so in this case, we are talking about non-polar molecule, comparison between non-polar molecules. If you go down group 17, you have fluorine, chlorine, bromine, iodine. As you can see, the molecular mass increase going down the group. The boiling point increases as well. Why? Because of the presence of dispersion force. The dispersion force, the effect of dispersion will be greater if the number of electrons is greater, because there will be more electrons moving around in that particular molecule. If moving from left to right, right to left, it will increase the boiling point of the substance. Moving on to the next slide. Alright, different shapes. You see, different shapes of molecule also play a role in the strength of dispersion forces. So molecules that form long chains will tend to have stronger dispersion force than more compact molecules with similar number of electrons. So let's just say we are comparing between butane and methylpropane. Both of them have actually the same number of electrons because they have the same number of carbon, same number of hydrogen. So this is C4H10, C4H10. We'll talk more about hydrocarbons. These are what we call hydrocarbons in the next few lessons. So essentially butane and methylpropane, even though both are C4H10, they contain 4 carbon atoms and 10 hydrogen atoms. You see the boiling point of butane is minus 0.5 Celsius. The boiling point of methylpropane is 11 Celsius. So what it says here, the higher boiling point of butane is because of the different shapes of the two molecules. Butane is a long molecule, methylpropane is compact. You see, being less compact and long means butane has more contact area to interact with its neighboring molecule to show stronger dispersion force. What this trying to say is that if you look at these two molecules here, A, which is butane, will has a greater dispersion force because there will be more interaction with neighboring molecules. So one butane molecule and non-butane molecule will have more interaction because in this case butane is less compact and long as compared to methylpropane, which is more compact. There will be less interaction with other molecules, and that is the reason why the boiling point of butane is greater than the boiling point of methylpropane. So methylpropane boils at minus 11 Celsius and butane boils at minus 0.5 Celsius. The reason is because of dispersion force. So we have to be very clear. When you talk about dispersion force, it can change depending on the size of the molecule. It can also change depending on the shape of the molecule, if the molecule has similar number of electrons. Moving on to the next slide. Alright, we are almost there. So what this is saying is that we are comparing between polar molecules. So let's say you are comparing between hydrogen chloride, hydrogen bromide, hydrogen iodide. Bear in mind, hydrogen chloride, hydrogen bromide, hydrogen iodide, they do have something in common. They are polar molecules. They have difference in electronegative value, and they do not form hydrogen bonding. Okay, they do not form hydrogen bond. So in this case, hydrogen chloride is the most polar of this molecule, therefore it has the strongest dipole-dipole force. But because hydrogen iodide, in this case, hydrogen iodide has the highest boiling point because it has a higher, it has a larger molecule and therefore a stronger dispersion force. As you can see in this particular diagram at the bottom, hydrogen chloride, hydrogen bromide, hydrogen iodide, the molecular mass increase going down. The hydrogen iodide has the greatest molecular mass followed by hydrogen bromide, hydrogen chloride. We know number of electrons is the greatest in hydrogen iodide followed by hydrogen bromide, hydrogen chloride, and we know that the boiling point in this case is the greatest is in hydrogen iodide. You may predict saying that hydrogen chloride should have the highest boiling point, but that is not the case, even though it's the most polar, because of the presence of dispersion force. So dispersion do play a role. If all of them in this case are polar molecule, dispersion force do play a role. The greater the size of molecule, the greater the dispersion force that is present, the greater the boiling point. So hydrogen iodide will have the greatest boiling point, followed by hydrogen bromide and hydrogen chloride. We are moving on to the next slide, which is the last slide. So what this says is that if you're going to include hydrogen fluoride into the equation, and as you're probably aware as well, when we talk about hydrogen fluoride, we know that hydrogen fluoride is HF. And what this is trying to tell you is that hydrogen fluoride is a polar molecule. It is a polar molecule. But at the same time, other than dipole-dipole force that it can form, it can also form hydrogen bonding, which means that you can sort of predict saying that hydrogen fluoride here actually has an even greater boiling point as compared to hydrogen chloride, hydrogen bromide, and hydrogen iodide. So from the last slide, we say that out of hydrogen chloride, hydrogen bromide, hydrogen iodide has the highest boiling point because it has the greatest dispersion force. But when we are comparing to hydrogen fluoride, because hydrogen fluoride here can form the dipole-dipole force, it can have hydrogen bond, it can also have dispersion, and that hydrogen bond do play a very big role. And it says hydrogen bonding between hydrogen fluoride molecules is stronger than dispersion force and the dipole-dipole forces in hydrogen chloride, hydrogen bromide, hydrogen iodide. And that is the reason why if you compare between hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide, we know that hydrogen fluoride has the greatest boiling point. Alright, so make sure you're very clear and do the questions that I've set on the school box page. So do complete the questions I set for this week. And then the next lesson, we'll move on to chapter 8. So I'll see you then.